Hi, and welcome everyone to the talk Partial Type Constructor. Before we start, I just wanted to remind you that for those who haven't already, to join the Slack channel. And for this talk, it is also possible to just unmute yourself during the talk and ask questions via Zoom. Or also, if you want to stay anonymous, you can ask over Slack and I will read your questions out loud for you. All right, now I'm very happy to introduce you to the speaker, Richard Eisenberg. He's a principal researcher at Tweak.io, and his work focuses on how to use static type systems to increase programmer productivity and also decrease the possibility of errors. Richard is one of the people behind the push and add dependent types to Haskell, and he's also a core contributor to the Haskell compiler GHC. And now, without further delay, Richard, you can take over.
Well, hi everyone. Thanks for joining us today. So yes, I just want to reiterate, I'm quite happy to take questions during the talk. Unfortunately, in this format, I can't sort of see a question mark on your face or a hand raised or something like that. So feel free. I'll try to pause a few times to ask for questions, but it's also totally socially acceptable to just start talking over me because there's not really another way of getting my attention. So just please feel free to do that. Before we get into the details of this, I just want to sort of preface, the ideas in this talk are not yet implemented. They are not yet even sort of proposed in the GHC proposals list. There is not a concrete plan to implement these ideas. And that's because I think in the end, the implementation would really depend under the hood on dependent types. And that's we're going to get the dependent types out there first. But this is meant to sort of get us to think about Haskell and to think about types in a new way. So we're just going to sort of live in this alternate universe for this talk where things are a little bit different than the universe we live in. And with the hope that maybe we can get a little understanding of our own universe by looking sort of through this sort of dark mirror. Okay, so let's dive in. Oh no. I've hit the button to advance the slide and nothing has happened. Okay, I can click maybe. Okay, we'll see how that goes. So this all starts thinking about polymorphic data types. So here we have a polymorphic list type, and when we see a definition like this in Haskell, we expect it to work for any different element type, right? So if we look at, we could have a list of ints, we could have a list of bool, we could have a list of functions, we can have a list of some person type. And all of these work out just fine. That's what it means to have a polymorphic data type. We can store any of these in a list. And in fact, all the functions that we write over lists work over any of these specific kinds of lists. Now, if we look at a set data type, well, how is that going to work out? So we could think about, this is also parameterized. We might store different kinds of elements in a set. Well, a set of ints, well, that makes good sense. I can tell if I've already added 5 to the set that I don't need to add 5 again, right? One of the key aspects of a set is that it doesn't store the same element twice. We need to understand what same means. So set of int makes sense. Set of bool makes sense. A set of int arrow int doesn't make so much sense because we can't in general tell whether two functions are the same, at least not in any decidable way. So that's a problem. But a set of person, that still makes sense, right? And all of this comes down to the fact that sets make sense only for elements with an equality relation. I need to be able to tell whether two elements are the same before I can even think about what it means to have a set of those elements. Now let's think about an implementation of a set based on a binary search tree. So BST stands for binary search tree here. And so we can imagine all of these same questions. So it makes sense to have a binary search tree of ints. It's very easy to tell whether one int is greater than another. We can even have a BST of bools, be very small BST, I suppose, but we could imagine that. We could define an ordering relationship among the bools. Once again, on functions, this is now not really possible. And I'm going to say we also can't have a binary search tree of persons, right? Because no one person is greater than another. So we'll use this as an example of something that we don't have a comparison on. And that's because binary search trees make sense only for elements with a total order. right? For any two elements, we need to be able to tell whether one is greater than another. And so that's what would make sense for a binary search tree. So abstracting out these, or not abstracting, sort of repeating these ideas, right? So we have sets and we have binary search trees, and they only apply some of the time. And yet. So in Haskell, if we define a set, we can still write a function like this. We can check what the size of this set of functions is. And if we write this in Haskell today, that will actually type check. We could have an implementation based on our concrete representation of a set. If you want to, you can imagine it's just sort of a list with duplicates removed. That's fine for now. Yet I claim that the fact that this function is accepted is actually a bug, right? This function doesn't make any sense. Oh dear, this is the wrong type. It should be take a set to an int. There should be another arrow int at the end of that line. That's very silly. But in any case, this doesn't really, this isn't a good thing to accept, right? Because maybe it's this function that computes a size, but actually this should never be called because we should never have a set of functions to begin with. And so you might say, well, it's okay to accept something like this because nothing could ever really go wrong if we accept this. And I actually agree with that statement, that writing a function that works over sets of functions, nothing really goes wrong, but it's somehow a bit silly. So here's another example. So I could imagine another language where I could write a function, id maybe, that just returns its argument, but it has type maybe arrow maybe. And this is not a typo here. I meant to do this one. And if we look at this, GHC rejects something like this, but this is another case where nothing can go wrong. If I was allowed to write this, those of you who haven't seen the error, by the way, so maybe we normally have to say maybe int or maybe bool. Maybe by itself isn't really a type. So if GHC allowed a function like id maybe, still nothing can go wrong. But actually, we want to reject id maybe because it's meaningless. We don't want this code in our program because it can't contribute to any useful work. So what we really want to do is for the same reasons we want to reject id maybe, we also want to reject size. Size was a definition that even though nothing can go wrong, nothing can go right either. We're never going to be able to use a function over sets of functions to do useful work. And so why have we rejected id maybe but accepted size? And that's because without really realizing, we've assumed all type constructors are total. So what I mean by this is that we started with list, right? So list makes sense for any element type. Those other types that we looked at, set and BST set, don't make sense for any type. But just the fundamental structure of Haskell's type system assumes that all type constructors are total. In other words, any argument, any instantiation of those data types is allowed to make sense in Haskell. And I want to challenge that assumption in this talk. So there are actually many partial types, and so we've seen some examples here, but there's some more. So a U array is an unboxed array, and this makes sense for types that we have an unboxed representation. So we can have an unboxed array, a U array of int, but we can't have a U array of person because we don't know what an unboxed person would be. A state T, this is the state monad transformer, that really only makes sense if M there is itself a monad. Having state T over something that's not a monad, again, nothing really breaks, but we can't make good use of it. All of sort of the applications of the state transformer monad depend on having an underlying monad. A complex number really only makes sense for numbers, things that have a notion of addition and multiplication. A shared array, this might be a data type where we can put information in and it's shared among multiple different computers in a distributed system, but that only makes sense for types that are serializable in that system. Or maybe we have some notion of encrypted with the phantom parameter bits that says how wide the bit field is. But again, this is maybe our encryption algorithm only supports powers of 2 in this spot. And so having bits be 5 just doesn't make any sense at all. But none of these restrictions can be expressed in Haskell today.
Sorry, Richard.
Oh, yes, please.
There's a question in
Yes.
Slack, and the question is, are type families aren't necessary total, are they? Maybe you can clarify.
So that's a good question. So type families, type families suffer from a lot of these problems. I'm not going to really talk about type families so much in this talk, but a type family can be defined only over some types and not only over others. In Haskell today, if a type family is only partially defined, if you use it outside of its definition, it just sort of gets stuck and it becomes what some people call an exotic type. But there's actually a paper. Was this ICFP 17? Yes, I think it was ICFP 17 called Constrained Type Families, which is in some sense a predecessor of this current work that talks more about type families. So I should also say this, what I'm talking about today, this is a published paper with collaborators Mark Jones and Garrett Morris. It was presented at POPL earlier this year. So there's a full paper accessible from my webpage with all of these details. Any other questions right now?
No, everything's clear so far.
Okay, great, thanks. Okay, so there are many partial types out there. And so far we've sort of focused on eliminating bad code, but it's more than just static checks that I'm after. So some of you might be familiar with the fact that we might want to make set an instance of the Functor class, except that we're going to have a very hard time writing fmap. So there's no way of doing this in Haskell today. And because any operation that works on a set is going to have to use an eq instance, all of its functions are going to be constrained, and we're not going to be able to call those functions from fmap. So there's because fmap doesn't have the right constraints on it. So there's just no way of writing this instance today. I shouldn't say no way. There are workarounds. These have been proposed before. I could have a list of papers that propose other intricate details, intricate encodings to avoid this problem. I think our idea is sort of a little bit more all-encompassing. There's plenty of related work mentioned in the paper and other ways to solve this particular problem. So I don't want to get fixated on, oh, but there's a good way of doing that. I'm sort of proposing a new way of viewing the type system here that's a little bit farther reaching. Okay, so the key idea in our solution here, where the problem is, right, that we have these partial data types, but we don't really know how to reason about them in our language, is to use what's called a data type context. So Haskell GHC actually supports this syntax already, but we're going to sort of expand out what I mean by that over the next few slides. So where I can say that only if A has an ORed instance can we have a BSTA. So here I'm putting a constraint sort of between the word data and the definition of the type, saying that BST only makes sense when ORed A holds. Right. So that's the meaning behind this declaration. And actually, you can type this in today. So if I go and do that, and I put that in bst.hs and I try to compile, I get error, illegal data type context. Use data type contexts. Okay, fine. So I edit my file and I add the data type context extension and I try again. And then I get this. Data type context is deprecated. It was widely considered a misfeature and has been removed from the Haskell language. Although this is only a warning, so has been removed. We could argue maybe it hasn't quite been removed. What's also interesting is there's no way of disabling this warning. I cannot program with data type context without getting warnings. So in fact, if we dive into the GHC source code, the way that this information is stored is in a field called DC stupid theta. And throughout GHC, every time we work with a data type context, it is called a stupid theta. Theta is sort of the keyword within GHC for one of these constraint contexts. So, this is a little bit odd that here I am proposing a feature that is widely considered a misfeature. So what's going on? So it turns out that these data type contexts were not always stupid. So if we go back to the Haskell 1.0 report from 1990, that report says that this syntax, if we have a data type declaration with a constraint C, it declares that that type T at concrete arguments T1 through Tn is only valid where the constraint suitably substituted holds. Right? In other words, for my BST type, if I want to talk about a BST of int, I need to know that ORD int holds. If I want to talk about a BST of person, I need to know that ORD of person holds, which it won't. Interestingly, this text is missing from the Haskell 1.1 report just a year later. And the reason for that is that the designers of Haskell couldn't quite figure out a way of making this sentence into reality. So I want to go back and bring back 1990. I want to take this idea and make it real 30 years later. And I want to give data type context a sensible semantics. So this has really been sitting around for 30 years and it's sort of untackled. Okay, so why are today's contexts stupid? Why is it a misfeature? It's because they don't really work. So here, if I in Haskell today declare that BST is constrained by ORD A, I can still write this function f. So even though that BST person, that shouldn't exist, I can still write this function and there's no errors at all. Right? GHC will accept this, even though accepting this is a bug. So it doesn't really do the thing that it's meant to do, which is eliminate the possibility of BST person when BST person makes no sense. On the other hand, here, if I'm forcing a BST, and I just want to force that top level constructor, nothing recursive here, this looks pretty innocent. And yet, GHC today rejects this. This is no good because I don't know that there's an ORD instance for A, even though this looks pretty innocent. So these data type contexts don't really work out very well for us. And so what I want to reinterpret this, and I'm not going to go into the details of the current interpretation, which are a little bit strange. Instead, I want to focus on my new proposed interpretation, which is that just mentioning BSTA already requires an ORD A constraint. So if I imagine a function id BST, a function that takes a BST and just returns it, I'm going to say that this first type signature, even before we see a definition of the function, I'm going to say that this first type signature is in error, right? Because I don't know that A has an ORD instance. So maybe this BST makes sense, maybe not, I don't know. Instead, I will accept this second type signature. This one's okay because here I'm saying there is an ORD A instance. So even before looking at the implementation, I need to have this ORD A constraint just in the type signature, but for the rest of the type signature to make sense. So in practice, though, even as much as I said that this is really what I want to do, this is a bit redundant, right? If I can't ever talk about BSTA without having my ORD A constraint, then what I'm going to do is I'm going to say every time I mention BSTA in a type signature, we're just going to pretend that I have the ORD A constraint in there as well. So here's a concrete example. So I have a function f that takes a BSTA. Because BST has this ORD A constraint, just writing BSTA, this type wouldn't make sense without ORD A in it. So when I read the type, I'm just going to say, oh, the user meant to have ORD A there. Just like the fact that by writing a lowercase a in a type, of course the user meant to say for all A somewhere. GHC is happy to bring A into scope automatically in this type, even though we haven't asked for it. Similarly, we're automatically going to bring ORD A in as a constraint. So that means that this function here would actually be allowed. And looking up at the top of the slide, because ORD A is implied, sorry. And looking up at the top of the slide, actually this first signature that I said we would reject, we would accept, but there would be this implicit ORD A constraint. So we could make it explicit if we wanted, but we don't have to. And this is to make sort of users' lives better and to aid in backward compatibility. So then the real challenge in all of this is abstraction. But let me actually sort of before I go to this new section of the talk, let me pause, see if there are any questions, and do feel free to just unmute yourself and blast away.
All makes sense so far.
Okay. Yep. That sounds good. It's just sometimes people take a minute to find their mouse and click on the button and things. Okay, I'll carry on. So what about abstraction? So in this world where we have partial types, I've said sometimes BSTA makes sense, sometimes it doesn't make sense. But if I want to abstract over BST to some arbitrary functor f, say, then for FA to be a type, we might have constraints. Maybe FA makes sense, maybe FA doesn't make sense. So we need to know that A is in the domain of F, right? The idea of these partial type constructors is that some things will work and some things won't. So the way I'm going to write that is using this at sign and say that F at A must hold, right? So that's just all that means is that I'm writing out this constraint F at A is just the way of encoding A is in the domain of F. More broadly, for T1, T2 to be a type, T1 at T2 must hold. T2 must be in the domain of T1. So for a concrete type capital T, this at constraint is just a data type context. So the constraint BST at A, in other words, is A in the domain of BST? Well, that's just ORed A. So we can imagine some process where we equate these two constraints internally. And turns out that's rather easy to specify. So here's the typing rule. There's not going to be a great many typing rules in this talk, don't worry. But the idea is so if we're trying to know that the thing below the line is true, in other words, that tau1 applied to tau2 really has kind kappa 2, then we need it to be well-kinded. We need tau1 to have kind kappa 1 arrow kappa 2. We need tau2 to have kind kappa 1, right? This is just normal function application. But now on this third premise here, we also need to know that tau2 is in the domain of tau1. So this would become a new or a modified typing rule in our programming language that says every time we have a type application, not only do the kinds line up, but we also need to be able to prove this constraint. Here, P is sort of the set of things that we've already assumed. So these are constraints, like maybe we have ORed A in the context somehow, and delta is the assignment of type variables to kinds. And so this is our new application rule. Okay, let's look at an example. So there's a lift function. This is used for monad transformers. If you're not familiar with monad transformers, that's fine. It's just that it has a lot of type variables that get applied to other type variables. That's the only reason I'm using it here. So this has some constraints. Let's not worry about them right now. But then it takes an MA for some M and some A to a TMA for some T, some M and some A. So according to this elaboration scheme, where every time we mention a type, we're going to assume that the type is valid. So what that really means is that when the user writes this, this type signature for lift, what GHC would understand if we implemented this is that actually there's these extra constraints. M at A, that comes from the MA that we see after the fat arrow. We need to know that A is in the domain of M. But then we have T applied to M applied to A. So T must be applicable to M, and TM must be applicable to A. So one thing that's a little bit strange here is that suddenly these contexts have become order dependent, right? I can't even write TM is applicable to A unless T is applicable to M. So the order does matter here. But the idea is that all the user would write is the thing at the top, and GHC would understand this thing in the middle or at the bottom. Okay, so here's another place where this elaboration scheme really works out nicely. So here's the same old definition of functor. This is the real definition of functor as we know and love. But now in this slightly altered universe where we have partial type constructors, then the meaning of writing what FA is and what FB is slightly different, right? That only makes sense if A is in the domain of F and B is in the domain of F. And so just writing this regular old type signature for FMAP really means that the GHC would understand this new type signature where we have these extra constraints F at A and F at B. And what this means is that my instance for functor BST would now be allowed because these extra constraints would be ORed of A and ORed of B if F were BST. And that's exactly what we need to be able to write a functor instance over a binary search tree. So this would now be accepted.
Is it always sufficient to like all these examples that you show, but maybe you're going to go there anyway, but to have this at and then a concrete type? Would you ever have to say, oh, maybe introduce some sort of quantification in there, for all such and such f at such and such must hold?
So I think that some slides later on will answer that question, but
Okay.
please ask again if I misunderstood it, if the later slides don't answer that question, but I think we are going to go there.
Okay.
But I'm happy to take other questions also. Okay. Okay, so I want to talk a little bit about theory, but if in this little theory section it starts to get a little too deep, we'll pop back out and everything will be okay. One question is that here, if I'm describing this new fundamental concept of how types are applied to other types, how do we know that any of this makes sense? And the way that we know that is that we're going to take our surface language that has these funny partial types, and we're going to compile it into an internal language that doesn't have these funny partial types. So if we can have a translation from this surface language into a more standard internal language that doesn't have this partiality stuff, and we know that that more standard internal language has a well-defined semantics, then clearly it means that our surface language has a well-defined semantics. So this is sort of an approach toward type safety and toward rooting these new ideas in ideas that we already understand. But what's interesting is that the internal language requires dependent types. So this is what the internal language looks like. Again, the details are spelled out in the paper. The point that I want to highlight on this slide is that the rules toward the bottom are very standard. So in particular, let's look at the top left rule. So this is in my internal language. If I'm applying tau1 to tau2, then all I'm doing is kind checking. There's no funny extra, some extra constraint must hold it. We don't have to write that in the internal language because there's no weird partiality here. It is a dependently typed internal language, so we have this extra substitution stuff going on. But for in a dependently typed language, nothing here is unusual. And so again, the point of this is just to highlight that these rules at the bottom, if you've seen dependently typed languages before, these are not strange at all. And so it means that we can understand this new strange thing in terms of something that's, for those of you who don't know dependent types, maybe it does look a little strange, but it's for folks in type theory, this is not peculiar.
Sorry, Richard, before
yes,
you go
please.
on, there's another, so there's one comment. Someone thinks that the functor of BST is not a good example because it violates the second functor law. Maybe you can comment on that one, or
if you remind me of the second functor law, which I don't know off the top of my head, maybe I can answer.
So if you're currently also in the Zoom call, maybe you can just unmute yourself and ask later. And if not, I will go on to the next question.
Okay.
The next question is, will add detect the class C, that the class C has an instance? So for example, num at int, but not num at person.
So when we have num at int, now you're asking about whether int is in the domain of num. And we can imagine having partial classes, just like we can have partial data types, but that's more imaginative than we're being in this paper. So but maybe that may have been a typo. If you just want to think about num int versus num person, then the usual class constraint solver mechanism will sort of kick into gear and we'll be able to solve num int, but not num person. I hope I haven't misunderstood the question. So I think I'll move on for now, but please stop me if there's other questions.
Yeah, sure. All right.
Okay. Okay. So I said that we're going to compile this surface language with partiality into an internal language that doesn't have partiality. And the way that that works is that we're going to have explicit evidence for when an argument is in the domain of a function. So whenever we see f applied to a, then that's actually going to compile into f applied to a applied to d, where d is the evidence that f could have been applied to a. And so in this internal language, just saying fa on its own is always okay. But we're not going to be able to sort of go any further. We're not going to be able to make use of f applied to a without this evidence d that a is really in the domain of f. The challenge now is that previously, if we wanted to quantify over a type constructor f of kind star arrow star, well, now there might be any constraint c. So c here is a constraint that would apply to the argument. So that's the star. And then in the language of the paper, we're using O to refer to constraints. So we can think of O as the GHC type constraint, if you're, or the kind constraint, if you're familiar with that. Whenever we quantify over one of these type constructors, we also have to quantify over any constraint that it requires of its arguments. So just to give you a quick example of what this would mean in practice is, so here we start out with fmap. So fmap has this very nice type. And then we're going to elaborate that out to this second type here. So all I've done in this elaboration is I've explicitly quantified over the type variables f, a, and b, and given they're written in their kinds. And I've also added the constraints f at a and f at b, because f is applied to a here and f is applied to b. And so we need to know that a and b are in the domain of f. And then that compiles to this larger type, where what we first have to do is we have to say, well, this f, I don't know what's going to be required of f's argument. So there's going to be some constraint c that's going to be required of any of f's arguments. So we have to quantify over that. Then we can quantify over f. But now let's look at f's kind. So f takes some argument a of kind star, but now it needs to know that that constraint holds of a. So in the concrete case, let's say f is bst. If f is bst, c would be ORed, right? So that's the constraint. And then the kind of f is, well, it takes some argument a, let's say int, but then it has to take an ORed int dictionary or an ORed int constraint before it's sort of a full type that we can use. So that's this funny kind of f. Then we take concrete a and b that we want fmap to work at. Functor now doesn't just work over f, but it has to work over c as well. Then we need evidence d1 that c holds of a. We need evidence d2 that c holds of b. In other words, this is the ORed a and ORed b constraints in the BST example. And then we get a function a arrow b, but now instead of just fa and fb, it's fa d1 and fb d2. Note that if we didn't have d1 or d2, there's no way that we could finish off this type because fa has the wrong kind to be on either side of an arrow. So we need the d1 to get the kinding to work out to be able to put this on either side of an arrow. Again, I expect that there's a fair number of people that are rather confused at this point. I'm happy to go back over this. But this is understanding this particular slide is not key for sort of understanding the larger picture. Here's the compilation algorithm. It turned out to be rather more complex than we thought at first. So this is not particularly easy to figure out, but it exists. We have it. We've proved that it's correct. And we proved that it's correct through this compilation. So I'm going to just move forward one slide and dim out the parts that we don't really want to care about. So what this is saying is that if some expression capital E has some type sigma, then it will compile down to some internal expression E prime. And if that can happen, then that means that E prime is also well typed. In other words, every initial expression that we have in our surface language, if it's well typed, we're going to get an internal language expression that is also well typed. And that's sort of the key step and the key proof about correct compilation here. I'm not so worried, at least in this proof, about whether the semantics are preserved. That's not, or rather the runtime behavior is preserved. That's not really called very much into question by what we're doing here.
Richard, can I ask a question?
Yes, please.
So the way that you described the add operator was like, is this thing in the domain of the function?
Yes.
But in a sense, that is precisely what a type system gives you, right? Right. That's, I mean, if I apply a function from int to something, I mean, I can only apply an int because the domain of this function is int, right?
Yes.
And so initially, I was expecting you to introduce some sort of, I don't know, some sort of refinement of a kind, basically, right?
Yes.
And you've done that. Now that you've shown the lower level language, that's precisely what it is, right? I mean, that f of what was it? A of kind star to C of A to star, that is precisely a refined kind.
Oh, hold on, I'm trying to get there in my slides. Yes.
Yeah. So to me, the lower level language here seems sort of more natural than the service language. Is there a reason why I'm sure you've thought about it, but why not introduce sort of a more like at a service language, like a refined kind, right? Not kind star, but the kind star where we have some constraints satisfied.
Yes, so we definitely did think pretty hard about going in that direction. And the truth is there's always really this tension around class constraints, right? So we could imagine, for example, instead of having a num constraint, just forgetting about partial types, instead of having a num constraint, we could imagine having a separate kind where all of these where int and integer and everything have that separate kind. And then we could imagine like the function plus to be for all a of the num kind.
Yeah, exactly.
So one challenge with that is it's hard to sort of combine things, right? Because of course int is a member of the num class, but it's also show and it's also ord and it's also a ton of other things. And so we could imagine some elaborate lattice, essentially, of different kinds with subkinding. But before long, we sort of end up with Java. And not that that's a different, or Scala does something similar. Not that that's a bad place to end up. I mean, that's clearly a successful model, but it's unclear how to make that work well with type inference. And so here it's all sort of one level up. So maybe we don't need as good kind inference or something like that. It is a viable alternative approach, and other languages have gone this way. So in particular, normally I like to think of Haskell as out in front in sort of its type system, but Java has had this since Java generics, right? Where you could have a type variable in Java that ranges only over subtypes of a certain class or of a certain interface, which actually has very much this flavor. Does it by quite a different mechanism, but it sort of accomplishes a similar goal. Does that answer your question?
Yeah, thank you.
Can I ask another question while we're on this slide?
Yeah. Oh, yeah. Oh, no, but now I've moved on. Let me go back. Yes, please.
Slide that we were on, which is that. So in the first type of fmap, you've introduced these. In the elaboration, you introduced these extra constraints: f at a and f at b.
Yes.
Do we also need functor at f?
So that's another good question. We could imagine having partial classes, which would then require a functor at f constraint. In that case, if functor were a total class, then it would sort of be trivial, and we wouldn't necessarily have to write it because we're not abstracting over functor itself. We could do that, and I don't think there's any problem with doing that. It just adds more clutter, and we don't have a use case for it. But I think that's totally consistent with everything else. Other questions? Okay. Okay, so we've gotten through compilation, so that's good. Okay, so now those of you whose eyes glossed over thinking about all of this more deep theory stuff, we can pop back in. So we actually have an implementation. I said we didn't have it in GHC. That's true. So this was we have an implementation in Hugs. Hugs is those of you who haven't heard of it. It's an alternative interpreter. It's basically just it's like GHCI, but it only has the I component. And it hasn't really been maintained for some time, but the initial ideas behind these partial types came from Mark Jones, who was the implementer of Hug. So he had sort of easier access to that than GHC, and did sort of a cheap and cheerful implementation. I've labeled it here in the slide as research quality, but it was enough to compile the entire base libraries. So this included 169 source files with 38,000 lines of code, just to see how does this actually work in practice. And I want to go back. This is going to be sort of the answer to the question from a little while ago about, what if there are extra constraints that we need? And this is going to hopefully answer that question as we look into this, because we were worried about an extra annotation burden. So here's one of the functions that was in sort of our test suite, as it were. Map and unzip m. So the idea here is that we have a monadic function f, and running f in the monad m produces a pair b and c. And we want to lift that to work over a list, and we want to get out not a list of pairs, but a pair of lists. And so here's the implementation of map and unzip m. It does the map and then it unzips. The problem is, so already, by the way, actually before we get to the problem, we can look at this type and we're going to get a number of these extra elaborated constraints, right? We need to know that m is applicable to a pair b and c. And we need to know that m is applicable to a pair of list of b and list of c. So we can see that right in the type. And so we can assume those constraints. But the implementation of map and unzip m actually introduces this intermediate result. This intermediate result has type m of list. Nowhere did we say that our monad m was applicable to lists. Maybe list is outside of the domain of m. And so in our implementation, in this Hugs implementation, this function signature and implementation actually failed, right? We got an error saying that we need this m at list of BC constraint, because there's no way from just the type that we would know we need this constraint. This arises only in the implementation, not in the type. And so our implementation flagged this as a type error. The good news is that the type error said, you need this constraint, and you just add the constraint and then everything was fine again. But what's very interesting in this particular case, and we saw this in some other cases too, is that this constraint is sort of incidental, that it is possible to write map and unzip m without getting this intermediate result. And the alternate implementation is actually faster. And so in some sense, the fact that we get a type error here is an indication maybe we're doing more work than necessary in computing an intermediate result that we don't need. And that's indeed the case in this example.
We have another question on
Yes,
Slack.
sure. Yes, please.
So the question is, does the extension also work with multi-parameter type classes? So is it, for example, possible to specify that the two parameters of some type constructor must be related by a two-parameter type class?
Yes, it does. And there's some subtle details about how that works, and that's actually in the paper.
All right, thank you.
Sure. So in our test suite here, we had almost 2,000 function definitions. In all of those definitions, only 20 needed extra annotations. The rest just sailed through. And in each time, the error was just, oh, you need to add this extra constraint. So you add the extra constraint and go on. But it gives you a chance to pause and and wonder, why do we need this extra constraint? Maybe there's a better way.
Another question popped in.
Yes, please.
So they ask if we are going to see an alternate implementation of the map and unzip m.
No, not in this talk. Is it in the paper? It might be in the paper, but if you go through and apply the function sort of one at a time, you can then manually build up the result lists. It turns out not very hard to do, but it just means we can't build map and unzip m quite so directly on map and unzip. It sort of means re-implementing parts of map and unzip, but actually in a way that fuses nicely.
It's leaking some implementation though, right? It's somewhat unfortunate.
Yes, and that's exactly what this slide is about. Yes. So when we write a type, that now in our alternate universe, our type will now constrain our implementation, because we can say write down the type of map and unzip m. Here's where we start and here's where we end. And maybe we have that type, and maybe we have some naive implementation, and then now later we can't go back and edit that implementation. And so is that a problem? Maybe it is. So the first thing I'd like to remark on is that this is very much the problem can also be seen in the way sets work. So we can imagine someone developing a set type where every operation on sets only requires an EQ constraint, right? Because the logical notion of set only depends on equality. And so we can imagine a whole set library, say, that just uses lists as the representation, that only has EQ constraints everywhere. And then imagine we publish that library and people use it and everyone's very happy. And then we realize, oh wait, we can have an asymptotic improvement if we just require ORD constraints instead of EQ constraints. But now, by changing the implementation of our sets, by making our sets more efficient, we have to change the types on all of our operations. And so in some sense, the fact that this standard set implementation in Haskell has ORD constraints everywhere, that's the implementation leaking out through the type. And so in fact, we have two different, we have containers and we have unordered containers. So we either need ORD or hashable. Either one is good, but we can't just have eq because we don't have an efficient way of doing it. And so with these partial types and the fact that we need these extra constraints, to me, it feels very much like this set requiring ORD, and that's leaking implementation details. Is that a real problem in practice? I don't know. It's a little hard to know how bad this problem really is without sort of a proper implementation and time for package authors to release their packages with certain types and then realizing, oh, but their types, aren't the right constraints and they can't then modify their implementations. So it is a concern of our approach, but I guess my claim is that it's not a concern that's unique to our approach.
And maybe going back to my earlier question, but could you say, like in your map and unzip m, could you just require somehow, I mean, I don't care what I'm going to apply m to, I want it to be in domain, right? I want it to be total.
Yes. So I don't have an example of that in the slides, but yes, you can. So using the quantified constraints extension, it's quite easy. You just say for all A, right, F applied to A. And so we could imagine encapsulating that in some sort of total right, constraint, and then we could require that an F be total, right, and that works.
Right. Nice.
Okay, so I'm just going to plow through. I have one more slide. So there's some related work. So I mentioned a little bit about Java and Scala's bounded polymorphism. That's a really different approach. Again, it's unclear how to take sort of that more subtyping approach and work it with type inference that initially was sort of born from the Hindley-Milner style. ML modules, right? We have these, they're called functors in ML, but that idea of functor is quite unrelated to the idea of functor in Haskell. And those can sometimes be constrained in a certain way. In a way that we detail in the paper, it's not quite as related as ML enthusiasts might think. Dana Scott has something called eLogic, which has existence constraints, very similar to our @sign constraints. It's a common question, oh, what about GADTs? And I claim that GADTs are orthogonal in that these partial types are useful whether or not they're GADTs. GADTs are useful whether or not they have partial types. And actually, we can have partial GADTs, and that's also useful. So the idea is that a partial type, the type itself is either valid or not, whereas GADTs are more about whether they're inhabited, right? So we might have, using a GADT, we might have an uninhabited type, but the type makes sense. Whereas here I'm talking about types that don't even make sense. The paper also outlines other approaches to partiality, and there's a lot of connections with our earlier work on constrained type families, which is sort of a similar idea, but in the world of type families instead of data types. But there's difference in the details. And I think that's all I've got. So I'm happy to stick around and answer any more questions.
Hey, so thanks for the talk. This is some fantastic work. I was the person who asked the question about the second functor law. So
please.
So let me try to explain this. So the second functor law is the composition law that when you say that fmap applied to f point g, that's the same thing as fmap f point fmap g, right? So when you
hold on. I need to write that down. I can't think that way. Just say that again.
So you have fmap open parentheses f point g close parentheses is equal to fmap f point fmap g.
Oh yes. Okay, that makes a lot of sense now. Yes, good.
Right. So if you add this constraint to the functor type class, what happens is that you get these additional OR constraints, for example, for binary search trees. And now suddenly you can stick f and g in there, and f may discard some information, and while doing that, change the structure of the BST. And changing the structure of a data type is usually not allowed in a functor. At least the way we think about functors in Haskell, because all of those are like endofunctor functors in Haskell. So you suddenly may get an instance that looks correct, but it actually violates the law because you stuck in some weird functions.
So I guess my question is, I'll sort of respond with another question, which is, what does equals mean?
So equals in that sense, I think, means the equals from a fast and loose reasoning, I suppose. So
yes, but I guess I would say so. I agree that the two different f maps, or the two different sides of the equality here, might lead to different internal structures.
yes,
but there should be no way other than maybe sort of measuring performance or something, and you could argue that that's important, but there should be no way sort of within the language to observe the difference between the two sides.
I'm not entirely sure. I thought it might, but now that you mention it, it might not. Yeah. My point, I guess my point was more along the lines that I personally feel that the functor of set is not the best example as a motivation for this, because there's, I mean, you've mentioned a ton of other applications for this, which are really nice. But I think motivating this using a functor of set could be slightly dangerous.
Fair enough. So, you know, if I'm honest, I think the reason that the functor set is in there is it wasn't actually an initial goal. Our initial goal was about more static checks, but some people are not happy with just more static checks, right? We want to not just decrease expressiveness, we want to increase expressiveness, and so we realized that there was actually this very nice way of increasing expressiveness also. So our primary motivation was more about decreasing expressiveness than increasing.
Right. Yeah, makes total sense. Thank you.
Okay, sure. Okay, so now I can.
Are there cases where, so in the map and unzip M example, there was like a bunch of constraints that M needed to, like a bunch of arguments that needed to be in the domain of M. And then I asked you, okay, could we say M must be taught? I said, okay, yeah, quantify constraints, help there. Are there examples where, because in that particular case, you could have added the constraint that you needed, right? Okay, it's very clear. This particular constraint is missing. Okay, added, fine. Are there examples, and this was, I guess, my earlier question, where it really must be universally quantified, where, I don't know, I'm like, just kind of breaking my head, like it's going lots of levels up, but are there examples where it really, because of, I don't know, some sort of, I don't know, like at the level of types, maybe you have a perfect tree or something, right, where you have nested occurrences at different types, where there isn't a single set of arguments. It really must be polymorphically or universally.
Yes, we encountered one, not in our sort of test bed, but in our sort of idle thinking about this. Rows, sort of, if you have like a rose tree that's based on some internal functor, I think, or something. So a rose tree here. I'm now in the Slack window. So those of you who don't know, so data rows, a typical rose tree is something like is that, I think the definition, oh no, it would be not, oh wait, Slack is, oh Slack, what did you do to yourself? No, Slack, no. When I hit press up in Slack now, because it updated and made itself worse, I can't edit the thing I just typed. Oh, why does everything always get worse over time? Okay, so this, well, oh no, I did it wrong. Oh God. Okay, so that might be the definition of a rose tree, but we could imagine a generalized rose tree, which looks like this. And here, oh no, that's not quite right. I mean f of g rows of f of a, something like that. Yeah, no, I know I can edit, but it doesn't immediately go into edit mode. I have to now press E to say to Slack that I can edit. It's very silly. So here, I think to do meaningful operations over this G rows, you would need to have, you know, like if we wanted to, you know, count, we might need to have something like this. You know, to say that it's total over everything. And I don't know if we'd be able to define count without something like that.
Yeah, and there's no way this could ever be inferred either, probably.
Probably not. No, that would be a challenge.
Yeah.
I mean, the good news is that it's fairly easy to write this, and we could even write right, and then so anyone can just write total f when they need to. Okay, so Lars comments on Slack here. F is the constructor around the new type, or G, okay, so it goes in and out of the new type. Ah. No, I don't see the problem in that example. So you'll end up with like your intermediate tree in fmap f.fmap g is gonna, you know, there's an intermediate tree in there, and it's gonna have like the different ORD instance, but then when the second fmap is gonna rearrange things correctly. I mean, maybe you're imagining a functor instance for BST which just edits nodes directly without, say, rebuilding the structure. But I'm not thinking that. That would be an incorrect functor instance.
Maybe just a quick side note for the people still watching on YouTube, especially. We're currently discussing, some questions on the Slack. So maybe if you haven't joined already, you can join, and maybe it will make more sense.
Yes, sorry about that, Simon.
I'm sorry. It was my intention to crash the entire thing. I guess we can discuss this offline.
Sure.
And yeah, happy for anyone else to have questions, of course.
So I don't know. Are there other questions that that arose?
Big question about coercible, which is written in the Slack. But yes, is there an interaction here with roles?
Oh dear.
What happens if you have a representational role on a data type?
So if you have a representational role, what kind of interaction are you worried about? To me, it doesn't actually, roles always sort of strike me in the heart a little bit, but not here. What are you worried about?
So if you have if you have a data type that isn't total, then presumably it can distinguish between different types that are representationally equivalent. So you might define a new type age of int, and then have a data type that was defined on age but not defined on int.
Yes.
Does that therefore imply that it somehow always has to be nominal?
Yes, that's an interesting question. I don't think that's one that we've thought about before. So my first response would be that role inference would, so whenever you use a class constraint in a data type, that will by default mean that you infer a nominal role for that parameter. So this is no different. But it is possible with incoherent instances to declare that a class has representationally rolled parameters. And so you can avoid that complication. And then, yes. I think, though, if you've done that, you get what you're asking for. As in, if I have a class C that takes one parameter A, and I declare when I define C that its parameter is representational, but then I go ahead and write an instance for C age, but not for C int, I've done something silly. And so I'll get maybe silly behavior, but I'm okay with that, right? Normally, every class will have a nominal role on its argument, in which case everything works out just fine. So I think that this is only, people who start to abuse GHC may get strange results, but it's okay.
Okay, thanks. That makes sense.
I don't think you'll ever get a segfault. It's a good question though. Hadn't thought about that. Okay, so I see there's a few other questions that came up in Slack. Okay, multi-parameter type classes I've answered, map and unzip M. It's a question about type theory. That is a very good question. Could you at some point give a talk or workshop about the type theory? Yes, no, that's an interesting idea, to just have sort of more of an of sort of introducing some of these, what does it mean to read typing rules and such, and how can we apply that? That might be a fun thing to do in the future. Yes, good idea. Thank you. Okay, just wanted to see if there's other sort of older questions that needed to be answered. Other questions here in Zoom?
So if there aren't any questions, I'm sure Richard will be still available in Slack, or yeah.
Well, I'm happy to sort of get into the weeds on this functor question for anyone who wants to remain. But those of you who aren't interested in that, feel free to wander off to other aspects of MuniHac. I assume is the MuniHac program is totally done for the night. Is that right?
There's some evening program, but it's more casual. So yeah, for anyone who wants to stick around for the functor question, feel free to do so. I will leave the meeting open. And yeah, I want just to thank you already, Richard, for the talk. Yeah, and also thank you for participating and watching for all the people viewing. And I will now close the live stream, I think. And for anyone interested still in the discussion, feel free to join via Zoom. Thank you.
Okay, thanks so much for moderating, Simon.